example. This is also an extension of this graph. Just circuit is added here. See, I painted with color 1, second in the adjacent vertex with color 2. Here I can paint with 1. Okay, see, one more I'm drawing. We'll paint here. I'm painting with color 1, 2, and one more here. I am painting with color 1 itself. What happens, we'll see. This vertex is adjacent to the vertex which are colored with 1 and adjacent to the vertex which is colored with 2. So we have to take a different color. I'll take color 3. Now these two vertices are adjacent to color 3. I can take here color 1. This vertex is 1 and this vertex is colored with color 3. We have to paint this vertex. And this last vertex is adjacent to the vertex which is colored with 1 and colored with 3. The only remaining color is 2 or other. I'm taking 2 because we need a minimum number of color to find the chromatic number. I'll paint 2. So the minimum number of colors required to paint this graph is 3. This is one way. This is one more way to paint the or color the graph. Here minimum number of colors required is 3. So the graph is 3 chromatic. Chromatic number is 3. Okay. I hope you are understanding. In this the chromatic number concept, we use the graph we assume that the graph is simple connected graph. Suppose if the graph is disconnected, if it has two components, the two components are connected graphs, right? So instead of considering the disconnected graph, we are considering only the connected graph. Also, we are not considering the self loop and parallel edges here because to prove some of the theorem, it will give us the contradiction. So we are restricting the self loop and parallel edges here. So in this full unit we are considering the graph means ಇಲ್ಲಿ graph ಅಂತ ಹೇಳಿದ್ರೆ only a simple connected graph. Here we are referring a graph means the graph is simple connected graph. ಬೇರೆ ಯಾವುದೇ ಯೂನಿಟ್ ಅಲ್ಲಿ ಪ್ರೀವಿಯಸ್ ಯೂನಿಟ್ಸ್ ಕಲ್ತಿದ್ದೇವೆ, ಗ್ರಾಫ್ ಅಂತ ಹೇಳಿದ್ರೆ ಅಲ್ಲಿ ಸೆಲ್ಫ್ ಲೂಪ್ ಬರ್ಬೋದು, ಪ್ಯಾರಲಲ್ ಎಡ್ಜಸ್ ಕೂಡ ಬರ್ಬೋದು. ಬಟ್ ಈ ಯೂನಿಟ್ ಅಲ್ಲಿ ನಾವು ಕ್ರೊಮ್ಯಾಟಿಕ್ ನಂಬರ್ಸ್, ಕ್ರೊಮ್ಯಾಟಿಕ್ ಪಾಲಿನೋಮಿಯಲ್ಸ್ ಅಲ್ಲಿ ವಿ ಆರ್ ಕನ್ಸಿಡರಿಂಗ್ ಗ್ರಾಫ್ ಮೀನ್ಸ್ a simple connected graph. That you have to remember. We'll continue. We'll see some of the observations related to the properly colored graph and are related to the chromatic numbers. A graph consisting of only isolated vertices. What is this isolated vertex? Isolated vertex means there is no edge incident on that vertex. If a graph consisting of only isolated vertices, the graph has only isolated vertices means the graph is null graph. There is no edges, only the vertices we are having. Then we can paint all the vertices with the same color because no vertices are adjacent to each other. So we can paint with only one color. So that graph which is consisting only isolated vertices is called as a one chromatic graph. It is a one chromatic graph. Second observation, a graph with one or more edge is at least two chromatic. A graph with one or more edges is at least two chromatic. If I have one edge, then at least two colors I need because these two vertices are adjacent. in any edges, the two vertices are adjacent, which are the end vertices of that edges are adjacent. So we have to paint with a different color. So any graph with one or more edges is at least two chromatic. That means at least two colors we need to paint such a graph. If I have only one edge, I need how many colors? I need color 1 and color 2 because they are this vertex and this vertex are adjacent, so I need different colors. So at least two color we need to paint such a graph. So it is at least two chromatic, they are saying. Two chromatic is also called as bichromatic. The other word for the two chromatic is bichromatic. Third observation, a complete graph of n vertices is n-chromatic because all its vertices are adjacent. Hence, a graph containing complete graph of r vertices is at least r-chromatic. That means, what is a complete graph? Complete graph means all the vertices are adjacent. That means, for every pair of vertices, there is edge in between the every pair of vertices in a graph. If I have four vertices, I need all the vertices has to be connected with one edge. This is a complete graph. Five vertices. If I have five vertices, 3, 4, 5. How we are drawing complete graph? I have to draw from here. Each vertex is connected by an edge. That means all the vertices are adjacent to each other. So we need different colors. This is a complete graph with three colors, three vertices, right? How many colors we need? If I paint with one color, here this vertex is adjacent to the vertex which is colored with 1. So I need one more color 2. Now this vertex is adjacent to the vertex which is colored with 1 and adjacent to the vertex colored with 2. So we can't use color 1 and color 2. We need one more color. I take that is 3. So this is a complete graph with 3 vertices. We need minimum 3 colors to paint this graph. So this is 3 chromatic. We have here I have showed the complete graph with 3 vertices is 3 chromatic. Now we'll see what is the chromatic number of the complete graph of 4 colors, 4 vertices. Complete graph with 4 vertices. I'm proving this observation, okay. This is a graph with 4 colors. Complete graph with 4 vertices. Now we'll see what is the chromatic number here. I'll paint this vertex with 1. Now here, this vertex is adjacent to the vertex which is colored with 1. So I can't take color 1 to paint this vertex. I have to take the different colors. I'll be taking it as 2. Next, this vertex. This vertex is adjacent to the vertex which is colored with 1. Also, it is adjacent to the vertex which is colored 2. Color 2. So, I have to paint with other than these two colors. I'll be taking it as color 3. Now, the remaining vertex is this vertex. This vertex is adjacent to the vertex which is colored with 1, and also it is adjacent to the what I see here. There is one edge between this vertex and this vertex. So here the last vertex is adjacent to the vertex which is colored with 2. Also it is adjacent to the vertex colored with 3. So I can't color this vertex with color 1, color 2 and color 3. I have to take a different color. So I am taking fourth color. So the complete graph with 4 vertices is 4 chromatic. In the same way, if we see the complete graph with 5 colors, that also 5 chromatic. 6 vertices is also 6 chromatic. A complete graph, because all the vertices are adjacent to each other, right? So we can't take the colors. If I have a complete graph with n vertices, then n minus 1 vertices are adjacent to this, the nth vertex, right? That n minus 1 vertices are colored with n minus 1 color. So since all the n minus 1 vertices are adjacent, I have to take a one more color, that is nth color. So I need n colors to paint n complete graph with n vertices. So it is n chromatic. If a graph containing complete graph, if in a graph, if I have a complete graph with r vertices, then I need at least r color to paint that vertices of the graph, because for the complete graph with r vertices, I need r color to paint that graph. So if the graph contains that complete graph itself, I need at least r vertices. ಈಗ ಇಲ್ಲಿ ನೋಡಿ, this is a complete graph, right? I'm considering this graph. This is a graph G. Graph G contains this complete graph. This complete graph with 4 vertices. We have seen that if the complete graph with n vertices is n chromatic, that means I need n colors to paint that complete graph. Here the complete graph with 4 vertices I have. At least 4 colors are needed to paint this complete graph. So the whole graph itself needs at least 4 colors to paint the full graph, all the vertices of that graph. At least r, if it has a complete graph with r vertices, it needs at least r, because that complete graph itself needs r colors to paint that. Then the graph containing that complete graph at least need r. It can take more than r, but at least it needs r colors to paint, not less than that. Circuit with n greater than or equal to 3 vertices is 2 chromatic if n is even, 3 chromatic if n is odd. Why n is greater than or equal to 3? We are not taking n equal to 1 because circuit with n equal to 1 and n equal to 2. Because the circuit with n equal to 1 andre ಯಾವ circuit? Self loop. A circuit with n equal to 2 andre ಏನು? The parallel edges. So that we are excluded from our graph. So we are taking n greater than or equal to 3. Circuit with n greater than or equal to 3. The chromatic number of that circuit is 2 if circuit has even number of vertices. If it has odd number of vertices, its chromatic number is 3. It is 3 chromatic. We'll see that. N greater than or equal to 3. If a circuit with, what is a circuit with 3 vertices? It is a triangle. We'll see what is the chromatic number of this graph. This is a graph with circuit with odd number of vertices. Because 3 vertices, it is odd. We'll see what is the chromatic number. This I'm explaining this one. If I take color 1, this vertex is adjacent to the vertex which is colored 1. So I have to take different color. This vertex is adjacent to the vertex which is colored with 1 and colored with 2. So I have to take different color 3. See here. Circuit with 3 vertices is 3 chromatic. Next we'll take circuit with 5 vertices, which is also odd, right? I'll take the circuit. How the circuit? 1, 1, 2, 3, 4, 5. We'll number this circuit. 1, these two are adjacent, so 2. Because they are not adjacent. They are not adjacent, so I can take 2. Next, here I am taking color 1. Here I am taking color 1. Can I take here 2, 1? No. Because 1 is adjacent. This is adjacent to the vertex which is colored with 1 and the vertex which is colored with 2. So I can't take color 1 and color 2. I have to take the different color 3. So I need at least 3 colors to paint this graph. So this is 3 chromatic. If I take the circuit with 7 vertices, even I need 3 minimum number of colors to paint that color that graph. If you take any odd number, the circuit with the odd number of vertices, you need at only 3 colors to paint that graph. Minimum 3 number of colors to paint that graph. So any circuit with odd number of vertices is 3 chromatic. If we take the circuit with even number of edges, I'll take 4 vertices. I'll paint this with 1. I can paint this adjacent with 2 because they both are not adjacent. Here I can paint with color 1 because this is not adjacent to the vertex which is colored with 1. So I can give color 1 here. The minimum number of colors required to paint this graph is 2. So this graph is 2 chromatic. If you take any circuit with even number of vertices, you will get it is a 2 chromatic itself. You can check using the examples. Next we will see theorem. Every tree with 2 or more vertices is 2 chromatic. We have to prove that every tree with 2 or more vertices is 2 chromatic. What is tree? Tree is a connected circuitless graph. And also we know that for every pair of vertices in that tree, there is one and only one path between them. That we have studied in the concept what we studied tree, in the concept of tree. We have seen many theorems. Some of that concept we are using here. Okay, we'll see. What is the proof? I'm considering a tree T. Let T be a tree. I'm naming that tree as T. Select any vertex B in the given tree T. T is also a graph, right? I can take any vertex. Consider T as a rooted tree at vertex V. What is a rooted tree? ರೂಟೆಡ್ ಟ್ರೀ ಅಂದರೆ ಅಲ್ಲೊಂದು ವರ್ಟೆಕ್ಸ್ ಇರ್ತದೆ, ಆ ವರ್ಟೆಕ್ಸಿಂದ ಬಾಕಿ ಎಲ್ಲ ಎಡ್ಜಸ್ ಪಾಸ್ ಆದ ಹಾಗೆ ಒಂದು ವರ್ಟೆಕ್ಸನ್ನು ಮೇಯ್ನ್ ಆಗಿ ನಾವು ತಗೊಳ್ಳೋದು. ಎನಿ ಟ್ರೀ ಕ್ಯಾನ್ ಬಿ written as a rooted tree by taking one vertex as a root, as its root. And considering V as a root of that tree T. See here. The example, this is a tree, right? Circuitless connected graph. Here, this vertex I am taking it as a root. ಈ V ಇಂದಲೇ ಎಲ್ಲ ಪಾಸ್ ಆದ ಹಾಗೆ ಉಂಟು, ಎಲ್ಲ ಎಡ್ಜಸ್ ಕೂಡ ಪಾಸ್ ಆದ ಹಾಗೆ ಉಂಟು. ಸೊ ಇದನ್ನು ನಾನು ರೂಟ್ ಅಂತ ತಗೊಂಡಿದ್ದೇನೆ. Consider T as a rooted tree at vertex V. Now paint V with color 1. We have to paint V with color 1. See here, I have painted V with color 1. Okay. Now paint all the vertices adjacent to V with color 2. We have to paint all the vertices which are adjacent to V with color 2. See. How many edges are adjacent to? How many vertices are adjacent to V? 1, 2, 3. 3 vertices are adjacent to V. We have to color the vertices which are adjacent to V with color 2. I have colored here. All these 3 vertices which are adjacent to V is colored with color 2. Next, paint the vertices adjacent to these vertices just colored with 2. Now I have colored to write some of the vertices which are adjacent to V, that I have colored with 2. Now we have to color the vertices which are adjacent to that vertices which we colored with 2 using color 1. We have to color the vertices which are adjacent to the vertices which we colored with color 2 by the color 1. You understand? See here. We have to color the vertices which are adjacent to these vertices. I have colored by 2, right? And that vertices we have to color with 1. The adjacent vertices to these vertices we have to color with 1. Which are adjacent to this vertex? There is no adjacent vertex, right? See here. Which are adjacent? This vertex and this vertex. We have to color with color 1. Next, this is also adjacent to this vertex V, which is colored with 2. For this, we have 2 vertices are adjacent. We have to color that vertex with 1. Next, continue this process until all the vertices in TR is colored. TR colored. Continue this process until all vertices in T are colored. What we have to do? Where we reached, we colored till here. Correct? No. That is what we can do. Next, which are adjacent to the vertex which are colored with 1, right? That you have to paint with color 2. See, this is the vertex with color 1. The adjacent vertex to this is 2. We have to color that with color 2. ಯಾವುದೆಲ್ಲ ಕಲರ್ 1 ಕೊಟ್ಟಿದ್ದೇವಲ್ಲ ನಾವು, ಅದಕ್ಕೆ ಯಾವುದೆಲ್ಲ ಎಡ್ಜಸೆಂಟ್ ಆಗಿ ಉಂಟು ಅದಕ್ಕೆಲ್ಲ ಕಲರ್ 2 ಕೊಡೋದು. ನೆಕ್ಸ್ಟ್ ಸ್ಟೆಪ್ ಏನು? ಕಲರ್ 2 ಈಗ ಹೊಸದಾಗಿ ವರ್ಟಿಸಸ್ಗೆ ಕಲರ್ 2 ಕೊಟ್ಟಿದ್ದೇವೆ, ಅದಕ್ಕೆಲ್ಲ ಅದರ ಎಡ್ಜಸೆಂಟ್ ವರ್ಟಿಸಸ್ಗೆಲ್ಲ ಕಲರ್ 1. ಹಾಗೆ 1 ಎಡ್ಜಸೆಂಟ್ ವರ್ಟಿಸಸ್ಗೆ 2. ಹಾಗೆ ಕಂಟಿನ್ಯೂ ಮಾಡ್ತಾ ಹೋಗುದು ಎಲ್ಲಿವರೆಗೆ ಗ್ರಾಫಿನ ಆ ಟ್ರೀಯ ಎಲ್ಲ ವರ್ಟಿಸಸ್ಗೂ ಕೂಡ ಕಲರ್ಸ್ ಬಂದಾಗ್ತದೆ. ಹಾಗಾದರೆ ನಾವು ಎಷ್ಟು ಕಲರ್ಸ್ ಯೂಸ್ ಮಾಡಿದ್ದೇವೆ? We have used only color 1 and color 2, only 2 colors. What we have to prove? We have to prove every tree with 2 or more vertices is true chromatic. ಅಂದರೆ 2 ಕಲರ್ ಮಿನಿಮಮ್, ನನಗೆ 2 ಕಲರ್ ಸಾಕು ಆ ಟ್ರೀಯನ್ನು ಕಲರ್ ಮಾಡಲಿಕ್ಕೆ, ಪ್ರಾಪರಾಗಿ ಕಲರ್ ಮಾಡಲಿಕ್ಕೆ. ನಾನು 2 ಕಲರಿಂದ ಖಾಲಿ 2 ಕಲರ್ ಯೂಸ್ ಮಾಡಿದ್ದಲ್ವಾ ಈಗ ಕಲರ್ ಮಾಡಲಿಕ್ಕೆ. ಬಟ್ ಅದು ಟ್ರೂ ಕ್ರೊಮ್ಯಾಟಿಕ್ ಪ್ರೂವ್ ಮಾಡಬೇಕಾದ್ರೆ ಪ್ರಾಪರಾಗಿ ಕಲರ್ ಆಗಿದೆ ಅಂತ ಗೊತ್ತಿರಬೇಕು. ಪ್ರಾಪರ್ ಆಗಿ ಕಲರ್ ಆಗೋದಂದ್ರೆ ಏನು ಅಂದರೆ ಯಾವುದೇ ಅಡ್ಜಸೆಂಟ್ ವರ್ಟಿಸಸ್ಗೆ ಸೇಮ್ ಕಲರ್ ಇರಬಾರ್ದು. ಸೇಮ್ ಕಲರ್ ಇರದಿದ್ರೆ ಅದು ಪ್ರಾಪರ್ಲಿ ಕಲರ್ ಆಗಿದೆ ಅಂತ ಅರ್ಥ. ಮತ್ತೆ 2 ಕಲರ್ ಯೂಸ್ ಮಾಡಿ ಕಲರ್ ಮಾಡ್ಬೋದು ಅಂತ ನಾವು ಈಗಲೇ ಪ್ರೂವ್ ಮಾಡಿದ್ವಿ. ಇಲ್ಲಿ ನೋಡಿ, ಕಂಟಿನ್ಯೂ until all the vertices in T is colored. Now in T, vertices which are of odd distance from V have color 2, and V and vertices which are of even distance from V have color 1. Then in T, vertices which are of odd distance from V have color 2. V ಇಂದ ಆಡ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ ಯಾವುದೆಲ್ಲ ಇದೆ ಅದಕ್ಕೆ ಕಲರ್ 2 ಇರ್ತದೆ. ವಿ ಮತ್ತೆ ವಿಗಿಂತ ಇವನ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ ಯಾವುದು ವರ್ಟಿಸಸ್ ಇರ್ತದೆ ಅದಕ್ಕೆ ಕಲರ್ 1 ಇರ್ತದೆ ಅಂತ. ವಾಟ್ ಈಸ್ ದ ಡಿಸ್ಟೆನ್ಸ್? ದ ಮಿನಿಮಮ್ ನಂಬರ್ ಆಫ್ ಎಡ್ಜಸ್ ರಿಕ್ವೈರ್ಡ್ ಟು ರೀಚ್ ಫ್ರಮ್ ಒನ್ ವರ್ಟೆಕ್ಸ್ ಟು ಅದರ್ ವರ್ಟೆಕ್ಸ್. ಇಲ್ಲಿಂದ from here to here I need how many vertices? 1 and 2. I need 2 edges to move from this vertex to this vertex. So the distance is 2. That is even. ಈ V ನಿಂದ ಆಡ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ ಯಾವುದೆಲ್ಲ ಇರ್ತದೆ ಅದರ ಕ್ರೋಮ್ಯಾಟಿಕ್ ನಂಬರ್, ಅದರ ಕಲರ್ 2 ಆಗಿರ್ತದೆ. ವಿಚ್ ಆರ್ ದ ವರ್ಟಿಸಸ್ which are of even distance from V, they have color 1. ಇಲ್ಲಿ ನೋಡಿ, V ಇಂದ ಈ ವರ್ಟಿಸಸ್ ಇದು ಡಿಸ್ಟೆನ್ಸ್ 1, ಅದು ಆಡು, ಅದರ ಕಲರ್ ಏನು 1. V ಇಂದ ಇಲ್ಲಿಗಿರೋ ಡಿಸ್ಟೆನ್ಸ್ 1, ಅದರ ಕಲರ್ ಕೂಡ 2. V ಇಂದ ಇಲ್ಲಿಗಿರೋ ಡಿಸ್ಟೆನ್ಸ್ 1, that is odd, the color is 2. and from V ಇಂದ ಇಲ್ಲಿಗಿರೋ ಡಿಸ್ಟೆನ್ಸ್ ಏನು 1 2 3, that is odd, also its color is 2. ಯಾವುದೆಲ್ಲ ವರ್ಟಿಸಸ್ ಆಡ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ ಇರ್ತದೆ V ಇಂದ ಅದರ ಕಲರ್ 2 ಆಗಿರ್ತದೆ. ಇವನ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ ಯಾವುದು V ಮತ್ತೆ V ಇಂದ ಇವನ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ ಇರುವ ಎಲ್ಲ ವರ್ಟೆಕ್ಸ್ ಇದು ಕಲರ್ 1 ಆಗಿರ್ತದೆ. ಬೇಕಿದ್ರೆ ಇದನ್ನು ಈ ಗ್ರಾಫ್ ಅನ್ನು ನೋಡಿ ನೀವು ಚೆಕ್ ಮಾಡಿ. Since there is one and only one path between any two vertices in tree, we have studied this, there is only one path between any two vertices in tree, because that is there is no circuit, right? So there we have only one path between every pair of vertices. No adjacent vertices have the same color. Why? See here. This is a tree, there is only one path, no adjacent. Since there is only one path, no adjacent vertices have the same color. See, if this vertices have 1, this is adjacent, so 2. This is adjacent, I can give 1. You can observe that no two adjacent vertices have the same color. You can observe here too, because the first vertex we have painted with colored with 1. The adjacent vertices to that we are colored with 2. ಮತ್ತೆ 2ಗೆ adjacent ಇರುವುದಕ್ಕೆಲ್ಲ 1 ಕೊಟ್ಟಿದ್ದೇವೆ. ಮತ್ತೆ ಎಲ್ಲ ವರ್ಟಿಸಸ್ ಪೇರ್ ನಡುವೆ ಒಂದೇ ಪಾತ್ ಇರುವ ಕಾರಣ ನಾವು ಮಾಡಿದ ಪ್ರೊಸೆಸ್ನಿಂದ ಏನು ಹೇಳ್ಬೋದು ಅಂದರೆ ಯಾವುದೇ ಎಜಸೆಂಟ್ ವರ್ಟಿಸಸ್ಗೆ ಸೇಮ್ ಕಲರ್ ಬರಲಿಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ. ನೀವು ಆ ಗ್ರಾಫ್ ನೋಡಿ ಕೂಡ ಅಬ್ಸರ್ವ್ ಮಾಡ್ಬೋದು. ಸೊ here no adjacent vertices have same color. This means the graph is properly colored. Also we have proved that only two colors are enough to color the vertices or paint the vertices of that all the vertices of that graph. So the graph is true chromatic. The tree is true chromatic. The graph we are considered as tree. The tree is true chromatic. I hope you understood. See here. Next note, every two chromatic graph is not a tree. We proved that every tree is two chromatic, but the converse need not be true. Every tree is two chromatic, but every two chromatic graph is not tree. See here. This is a graph with two chromatic graph. It needs only two colors to paint, but it is not a tree because here we have a circuit. Next theorem. A graph with at least one edge is two chromatic if and only if it has no circuits of odd length. What we have to prove? The graph is two chromatic if and only if it has no circuit of odd length. We consider a graph G with at least one edge. Now we'll assume that the graph is two chromatic. What is two chromatic? Two chromatic means only two colors are enough to properly color that graph. What we have to prove? We have to prove there is no circuit of odd length. Suppose there is a circuit of odd length. What happens then? Then we need at least three colors to color the circuit. Why? See here in the observation, circuit with n greater than or equal to 3, if that n is odd, we need at least three colors, or that is three chromatic graph. Right? If the circuit, if a graph contains a circuit, that circuit with odd length, that circuit itself needs at least three colors to paint that graph. Sorry. Yeah. Using that observation, which contradicts that the graph is two chromatic, because if a graph has circuit of odd length, that circuit itself needs three colors to paint that circuit. Therefore, obviously the graph needs three or more colors for the proper coloring, which contradicts the fact that the graph G is two chromatic. So, therefore, G has no circuit of odd length. Our assumption, we have taken G has circuit of odd length, that is wrong. The graph G has no circuit of odd length. We'll prove the converse. What we have to prove? Assume that G has circuits of only even length. What is the converse part? The graph G has no circuit of odd length. That means G has only a circuit of even length. ಅಲ್ಲಿ ಆಡ್ ಲೆಂತ್ ಇದ್ದು ಸರ್ಕ್ಯೂಟ್ಸ್ ಇಲ್ಲ ಅಂತ ಹೇಳಿದರೆ ಗ್ರಾಫಲ್ಲಿ ಸರ್ಕ್ಯೂಟ್ಸ್ ಒಂದು ವೇಳೆ ಇದ್ದರೆ ಅದು ಇವನ್ ಲೆಂತ್ ಇದ್ದು ಮಾತ್ರ ಇರುವಂಥದ್ದು. G has circuits of only even length. Now, what we have to prove? We have to prove that graph is two chromatic. How to prove? We prove this theorem using by taking the spanning tree in that graph. Consider a spanning tree in that graph G. Now we'll using the coloring procedure, and from previous using the coloring procedure we'll color the spanning tree. Spanning tree is also a tree, right? It is spanning tree. It is a tree in a graph which contains all the vertices of the graph. Using the coloring procedure and previous theorem, we say that we can properly color T by two colors. We have proved that every tree is two chromatic. That means only two colors are enough to color the tree. Since spanning tree is also tree, two colors are enough to properly color the graph spanning tree T. Now we add chords to T one by one. What are chords? The edges of the graph G which are not in the spanning tree. To complete the graph for the spanning tree, we have to add the chords. Now one by one we will add the chords to the spanning tree. Since G had no circuits of odd length, we have assumed that there is no circuits of odd length. The end vertices of every chords are differently colored. Why? If I take this is a spanning tree, there should not be any circuit of odd length. This one. There should not be any circuit of odd length. This is a circuit of even length. If I color this 1, 2, 3, sorry 1, 3, 1, 2, 1, 2. See, this is a chord I am adding. Since this is a chord of the not even length circuit, the adjacent vertices have different colors. If I add the chord for the spanning tree, the adjacent vertices have different colors since it is a even length circuit. If it is, suppose if it is a odd length circuit, what happens? So this is a spanning tree. If suppose if I add this chord, what happens? 1, 2, 1. The adjacent vertices will get a same color. This only if the chord is chord is of the odd length circuit. But here no odd length circuit. All the circuits are of even length. So the end vertices of that chord have different colors in that spanning tree T. Thus G is colored with two colors. Only the colors what we used for the spanning tree is enough to color all the full graph, all the vertices of the graph, and also that are properly colored. Thus G is colored with two colors with no adjacent vertices having same color, that is G is properly colored with two colors. So G is two chromatic. Here we have proved the theorem. We have assumed that G has circuits of only even length, and we proved G is two chromatic. Next theorem, you don't have proof for this. If D max is the maximum degree of the vertices in a graph G, then chromatic number of G is less than or equal to 1 plus D max. If D max is the maximum degree of the vertices in a graph G. If any vertex have a maximum degree, if I is a if 3 vertices are there and one vertex has the degree 2, that is the maximum, then chromatic number of that graph is less than or equal to 1 plus 2. 2 is D maximum. You have to remember this. There is no proof for this theorem. For you, there is no proof. For your syllabus, they are not included this proof of this theorem. You just study the statement of this theorem. Okay, for this, we have completed today's class. Tomorrow I will continue the chromatic number concept itself. I hope you understood. We have seen proper coloring, chromatic numbers, an example for that, some of the observation, and we proved 2 theorems. Understand the theorem. It is easy to understand, but with the example you have to understand using the example you have to understand the concept. Take 2-3 examples, see what is the contradiction and all. I'll finish for this. Thank you. Ram Ram.